This morning it's my pleasure to introduce Dr. Michael MacCracken. Dr. MacCracken comes to us from Lawrence Livermore National Laboratory, where he is Deputy Leader of the Atmospheric and Geophysical Sciences Division. Dr. MacCracken did his undergraduate work at Princeton, received his PhD from the University of California, Davis, where he undertook modeling studies on various proposed causes of ice ages. At Lawrence Livermore, the related work that he has done has included modeling on the climatic impact assessment study, and since 1979 he has been the scientific director for DOE's CO2 climate research program. He also serves on the National Academy of Sciences panel on CO2-induced climate change. His topic today is climatic warming from increasing carbon dioxide concentrations. Dr. MacCracken.
Thank you. Late in the 19th century, it was recognized by some geologists that carbon dioxide was a component of the atmosphere that could have possibly induced some past climatic changes. It wasn't recognized quite then that man would have an influence, but then about 50 years ago, calendar suggested that man's emissions could actually be having an influence. That was dismissed, although some of you may have remembered reading when you were young, or I remember when I was young, reading in Popular Science and Popular Mechanics how CO2 was warming the world and we were going to melt ice caps and things. But the idea was basically dismissed until the 50s because there was so much carbon in the ocean that it was felt that the ocean could take up whatever man emitted. But over the last 25 years, there's been a lot of serious concern when it was recognized that that wasn't really true. And so some statements, rather provocative statements, have been issued by rather prestigious bodies that try and raise the fossil fuel issue. And as a result of statements such as this, there's been a Department of Energy research program for about the last 4 or 5 years. The CO2 problem was made one of the 2 environmental issues that was specifically mentioned in the Synfuels bill that went through Congress, the other being acid rain. It's also raised a lot of sort of popular interest, and the next slide shows what one company's view of the CO2 issue was and about what will happen. What I'm going to try and do today is cover some topics and try and put in perspective what's going to happen. I want to talk about the carbon cycle, what the basis is for the notion that carbon dioxide concentrations are and will be increasing. I want to talk about, provide a little background information on the climate. Most people are concerned about the climatic effects of what might happen. Then talk about the effects of CO2 on the climate and why this little bit of change in CO2 is able to have such an influence on the climate. There's been a lot of interest recently about searching for evidence that the climate is changing or has changed. And I want to make some comments on that and the difficulty of searching for that evidence. Finally, maybe a few implications about what this all means. Well, the fundamental hard evidence that CO2 is changing is shown on the next view graph, which is the longest continuous set of measurements that's been made. It's been made at Mauna Loa Observatory in Hawaii. Basically what it shows is a seasonal cycle where the CO2 peaks in about April of a year after the decay of all the vegetation, and it goes to a minimum through the growing season, and so is at a minimum in about October when the decay sort of process starts over again. So you see a gradual increase in the annual average from about 315 parts per million to, it's up at 340 now about, with a seasonal cycle imposed on that. Seasonal cycle is somewhat larger, somewhat north of Mauna Loa, It's considerably less in the southern hemisphere, where there's much less biosphere to interact with it. The average concentration in the southern hemisphere is a little bit below the northern hemisphere, lagging about 1 to 2 years, which is about the time that we know it takes for air to interchange based on radionuclide experiments. Just for later, well, for the next, as background for the next slide, let me give some units. These are in parts per million of volume. You can also think of them in terms of gigatons per hemisphere of carbon. I want to do that because that's what they talk about emissions in terms of. Gigatons is 10 to the 15th grams. It's sort of an inconceivable kind of number to me. But I'll be talking about it on the next slide and some stuff on carbon cycle. What's interesting is that if you look at the seasonal change, this is about 5 or 6 parts per million, which is equivalent of 5 or 6 or 7 gigatons of carbon. Okay, now I'll come back to it, but fossil fuel emissions right now are about 5 gigatons of carbon. So the seasonal change, everything you see in the northern hemisphere that grows basically, or that is grown from the winter to through the summer, all the grass and the leaves on the trees and the limbs and the increased limbs, not the standing carbon, but the annual growth is about equivalent right now to man's emissions within a factor of, I don't know, 25 or 50% or something like that. So that maybe gives you a feel for gigatons and the magnitude of man's impact on what's happening. The next slide shows the various reservoirs where carbon is stored. In the atmosphere, there's about, between the upper and lower atmosphere right now, about 700 gigatons. The living biosphere, standing living biosphere, all the forests have about the same amount. The soil has about twice that amount. Upper ocean is about the same as the atmosphere. And then the deep ocean has lots of carbon, and then there's lots in the fossil fuel reserves that exist here. And you can look at some of the fluxes. These fluxes look quite large compared to fossil fuel. Here they say 6. It's really, I think, been revised down to about 5 recently. But these interchanges that go on between the biosphere and the atmosphere, for example, based on, say, radionuclide studies of exchange rates and things, show quite large numbers. But a lot of that is just the respiration process. And so it isn't really the net growth. So that the 5 or 6 here is about equivalent to the net growth over a season in the northern hemisphere. There's also large exchanges with the ocean. In order to predict future carbon dioxide concentrations, what you want to know is how this system really works. A lot of these numbers are sort of estimates. So the information that exists are what the present concentrations have been. There are some indications of what past concentrations have been in the last century, when instead of 340 parts per million, it was probably around between 250 and 290. I'll come back to that. There are some recent ice core measurements shown on the next slide, which indicate what concentrations have been about during the last 10,000 years. They go down in the ice cores, they get the air out of the bubbles that are trapped in the ice cores, and they measure the carbon dioxide concentration of it. There's some large potential errors in some of that, and you have remelting and all kinds of other things. But they're starting to work out problems. So they think that the background concentration is about 300 parts per million. This is from Greenland, this is from the Antarctic here. This great dip that comes in the oxygen-18 isotope curves and in the CO2 is during the last major glacial cycle. So there's some thought that CO2 was actually less during the last glaciation. Whether that was a cause or a result of it is not at all clear. Another thing we know about the carbon cycle is sort of what's been happening recently. Well, in the past 100 years, you can reconstruct the emissions of carbon. The next view graph isn't really emissions, but it's world energy use, which is essentially the same thing. I won't go through a conversion to gigatons here, but what you can see is they've gone back and they've done a lot of compilations back to the middle of the last century on fossil fuel emissions. And you can see it's basically exponential, except for World War I, the Depression, World War II, and then this doesn't show it, but but in the later 70s, the growth rate has changed from about 4% per year to down to about 2% per year due to the price increase of fossil fuels. Another source of information is shown on the next slide, which is based on some isotopic ratios information that come basically, I think, from tree rings mainly. This information does. If you measure the carbon-13 in tree rings and then sort of try and extrapolate back to what the atmospheric value was, you get what these data points here. And that is, and so it's the carbon-13 in the atmosphere has basically been going down. And the question is basically why that's true. If you take the fossil fuel emissions, and it turns out plants differentiate in how much carbon-13 they have compared to what the atmosphere has. If you do just fossil fuel emissions and project back in time, basically from the present and go back, I guess, what you find is that you don't match the curves very well. I guess I start from the reference here. I'm sorry, I come forward. You don't match the data very well, and so everybody's sort of recognized that there had to be a tremendous injection of carbon also from the biosphere, the expansion of agriculture, the industrialization of agriculture, because you plow up, you cut down the forest, you plow the soil, you oxidize the humus. And so the next slide sort of shows what happens when you try and put all this together in terms of what they think fossil fuel emissions are. These are basically fossil fuel emissions, this exponential curve. And then this is what must have been true in the biosphere if the total information on carbon-13 was to be true. So that there has been probably a major increase from about 250 parts per million early in the last century due to man's activities on the biosphere. There aren't any measurements that go back there to say what the atmospheric concentration really was, so this is sort of derived information. There are some measurements back in here, but most of them were made in the industrial areas of Europe and were so subject to local sources that and there was so much scatter in the data, you really can't interpret them very well. Another way of figuring out how the carbon cycle works is to look at the various reservoirs, and one way is to look at the oceans. It turns out the nuclear tests of the 60s have been very useful in doing this. This is a profile in the Atlantic, meridional profile in the Atlantic of the injection of tritium into the ocean. Basically excess tritium, so from the nuclear tests, and you can see that at equatorial latitudes it doesn't diffuse down very far, get into the ocean very much. Where you have bottom water formation in the North Atlantic, you do get some rather deep injection. These measurements were made in 1972 and 3. The next view graph shows how it's changed. And there was a major measurement program in 1981, and they haven't, I don't think, redone the plots, but these are sort of the changes that have occurred. There's not much change in the lower latitudes where water is basically, deep water is coming up and rising to the surface, but in the North Atlantic regions where the surface water is sinking to the bottom, there have been deeper penetration of tritium. That gives one a reading of how fast the tracers can move into the ocean and basically how fast carbon dioxide can move into the ocean. Well, if you put these fluxes all into a sort of a summary estimate, and here we go back to this number of gigatons per year. Fossil fuel emissions, the best estimates are sort of 5.2 gigatons. The biospheric reservoir, there's a large range of estimates about what's happening, and it depends on whether people believe you're cutting down the tropical forests at rates that occur in some regions, or whether you're getting regrowth of forests in, for example, the northeastern region, which was cut down early in the century and is regrowing tremendously. So there's quite a range of estimates here. This is probably the best estimate. The oceanic estimate is reasonably well understood because of these radioisotope measurements, and the atmospheric increase is pretty well understood. The rate of increase per year in the atmosphere is pretty well measured. Now, if you try and add these up and see if you're in balance, well, if you add up the ocean and the atmospheric increase and equate them to fossil fuel, you're in good shape if the biosphere is doing nothing right now. But if you go out and talk to ecologists and people studying the forest and the tropics, most of them believe that there has to be a source here. If that's true, then we really don't understand this cycle quite well enough. But it's reasonably close, so it's within maybe 20% or so of understanding what's happening. Well, the question then what's going to happen in the future? And so people go out and make projections of future energy use, and the next view graph shows one of them. They're rather incredible numbers, to my way of thinking. A lot of this information comes from the United Nations, and there's a great sense that that information has a lot of political information behind it. That is, developing countries want to grow at 5% per year rather than have the capability of growing at 5% per year. So 5% per year gets built in. But if you look at per capita use, you see little change in North America. There's certainly some conservation, I guess, and growth will tend to balance out. But a lot of growth in some of the developing countries. And this is sort of a 50-year forecast where they're projecting 6 times as much energy, for example, in the developing parts of Asia. Whether there's the economic and social infrastructure to accomplish that is not at all clear, but those are the kinds of projections that exist. As you can see, basically global per capita use doubles and global population doubles, so that the total amount of energy use quadruples, and most of it will probably come from fossil fuel, although certainly there are other alternatives. One question that's come up a great deal is whether going to synfuels is good or bad. And just for reference, I can show you synfuels with respect to other things. The reason synfuels are more expensive in terms of the amount of carbon they put out is because it takes energy to produce them, and so that's basically included in this estimate. So this is really per 100 quads of useful energy out. They've actually used a good deal of energy to create the synfuels. But if you make calculations, any reasonable sort of U.S. program in synfuels isn't going to have much impact in terms of the global numbers that are considered. But I think the argument on the other side that is used by environmental groups is basically it's a symbolic issue. If the United States is going to start talking in the future about a CO2 problem, and yet is using using energy in a way that produces produces more carbon than it really has to, it's symbolically a bad thing to do. Well, so as a result, one makes projections about when CO2 is going to double. Estimates made in the early 70s with this historic growth rate of 4% per year led to a doubling early in the next century. If you don't change fossil fuel rate, if you keep it constant fossil fuel emissions here, basically after some time here, you don't double until way out in the 22nd century, I guess. I guess the current estimates sort of are looking toward a doubling late in the next century. That doesn't mean there aren't any problems till late in the next century in terms of climate, or aren't any issues, or aren't any effects, but that's just sort of a convenient number that people look at. Well, one might ask a question, is there anything we can do about it technologically to keep the CO2 from increasing? And it turns out, I guess most people's feelings are there's very little that one can do. Removing CO2 at the point of emission is just an extremely expensive process. Energy-wise, it takes one power plant to remove most of the CO2 from another power plant. And so it's not something you're going to do. Basically what you do, for example, if you take coal into a power plant, you're taking one carbon atom in. If you're going to create a calcium carbonate to take out, you're taking not only that carbon atom, but a calcium atom and 3 oxygen atoms out in your train. So it becomes very expensive and energy-wise, and just a tremendous amount of material. There is some thought about sort of injecting this material into the deep ocean, but gathering it is just inordinately expensive. Growing trees has been suggested. In fact, there's a sort of one of these, congressman is going to solve the problem by putting trees all along our interstate highways. I think you can get a feeling for that in terms of the seasonal change, how many trees that would really involve. It's just not something that's going to be accomplished. Once CO2 is in the atmosphere, it's kind of dilute. again, you can talk about trees, although you run into other problems of nutrients and other kinds of things. There has been talk about fertilizing the ocean, bring your oil tankers over and then running backwards with phosphorus or phosphates and stuff to put them in the ocean. I think unlikely. Certainly switching to other fuels or reducing CO2 fossil fuel emissions helps. Biomass will help, certainly, because that's basically taking carbon out of the atmosphere and so it doesn't add to the net total. And if you can use nuclear or solar or some way to make hydrocarbons from atmospheric CO2 or energy from the atmospheric CO2, you help. But it's it's not likely to be a problem that you're going to be able to prevent or innovate you prevent. Well, to summarize basically the carbon cycle aspects of it, this was a point made, as I say, 25 years ago that we're doing something that hasn't been done before. CO2 has probably been very high in past geologic times, but certainly not in past historic times. And so we're really doing a giant experiment, and the question is, what is the outcome going to be? The basic system that it will affect is the climate. And what I'll be talking about next is the climate system and some aspects about it. And first I ought to perhaps define my terms and what I mean. Climate is basically a measure of the probabilistic state of the atmosphere and the moments and the means and things. Where weather is a momentary kind of state of the system, I guess one of the little euphemisms or phrases about it is that climate is what you expect and weather is what you get, which puts it reasonably well. It's not a quantity. Climate isn't really very well defined, and in the National Climate Act, the Congress decided it wouldn't even try and define climate. It just used the word. Certainly, as we change the climate, the weather is going to change. But really what we're interested in terms of how we live in our lifestyle is what the climate is, what the needs are going to be in the moments and the changes in the frequency of climatic systems. Well, a climate system is an extremely complicated, involved system. This is just sort of one drawing of it, and I'll show maybe some others in a moment, that has a lot of things affecting it that one has to treat. Usually what's considered internal to the system is the atmosphere and the oceans, but with CO2 being such a long-term problem, you start having to worry about the ice and the state of what's happening on the land. But there are a lot of different things that can change and influence what's going to happen. Climates of the past have changed, and the next slide shows some of the factors that people have thought have influenced some of these longer changes. And there's certainly more. This is just sort of a list. But variation, this is a time scale across the bottom with a year being here and 1,000,000 years out here. But there's certainly a lot of things that can change. The composition of the atmosphere is what we're most interested in terms of CO2. But ice can change, positions of continents can change, just all kinds of things can have effects. And so if you look at information on the past climate system, you can see that the climate has actually changed. And this sort of goes back, increasing in order of magnitude each time in years. But the reason climate was sort of this is northern hemisphere basically, was warm in the 40s, kind of cold in the latter part of the last century, and has been cool recently. And I'll come back to an update of some of this information later. In terms of the last 1,000 years, however, we've been in a relatively warm period. There was what was called the Little Ice Age. Now, this information, a lot of it comes sort of from Europe, and it may be biased by Europe, and there's some question about whether it's a global phenomenon, perhaps. But it was kind of cool several hundred years ago, and then during the Viking period, it was almost as warm as it is at present. If you go back the last 10,000 years, you see we're still relatively warm, although it was a little warm, maybe warmer 5,000 years ago, and again, I'll come back to that in a moment. And then there was the last glacial maximum, which was about 15,000 years ago. And then you can go back 100,000 years. This is the last glacial maximum. We were relatively warm, and the last time it was as warm as it is at present was about 100,000 years ago. And then you can go back, again, 1,000,000 years, and one has glacial cycles. I don't want to go into how all this information is derived, but that's one of the great sort of mysteries and searches that exists. I think the thing to notice, though, is that if we increase 2 to 3 degrees, which is what is projected if one doubles CO2, you're going to get to a climatic state that is basically unprecedented in the last perhaps 100,000 years until you're back to here. The climatic optimum, which is this 5 to 7,000 maybe year period here, was maybe 1 or 2 degrees warmer, and there's people who are looking at that as an analog for the CO2 state. But in terms of man's history, being 2 to 3 degrees warmer is sort of going to be an unprecedented event. There's been some tendency to change the term unprecedented to mean bad or catastrophic. That isn't necessarily true. People are starting to try and decide whether it's actually good or bad to be warmer. I mean, if you tell the people in Chicago in the winter that it's going to be 2 degrees warmer, most of them would be delighted. On the other hand, if you look at the changes that have occurred over the last 10,000 years ago, 10,000 years, it turns out that the change in ocean temperatures, this is actually some measures of land temperatures and stuff, but the global average ocean temperature during the last glacial maximum was about 2 degrees cooler than it is at present. So 2 degrees for the global climate is a major kind of change that can occur. Let's talk a little about how CO2 affects the climate and how it enters in. Basically, it enters in as a factor in the radiative balance of the atmosphere by trapping radiation, basically long-wave radiation that's emitted from the Earth to space, by trapping it and making it harder to escape to space. So it's, I guess, sort of like adding insulation on the atmosphere. And I don't want to quite say greenhouse because that's not how a greenhouse works, but it's basically like adding some insulation on the top of a house. If one then does a test simulation where you take an atmospheric profile and double the carbon dioxide concentration, as shown on the next view graph, and I apologize here, I'm going to be switching units a little bit on you. The units here, 100 here is the solar radiation input, so this is 70% of the solar radiation. Basically, the Earth's energy balance, 100 units of solar energy come in, 30% is reflected, long-wave radiation balances the rest. The numbers outside of parentheses are what the normal fluxes are, 70 going to space. Note that the radiation from the surface to the atmosphere is actually larger than the radiation from the sun to the Earth, which is an indication of this trapping of radiation. The net flux from the surface, however, is pretty small. There's a lot of back radiation coming down from the atmosphere. And so one can look at the normal balances of what's happening here. In parentheses are what happens if you double carbon dioxide. And these changes look very small. That is, in the net, you're increasing the trapping in the troposphere by only the equivalent of 1% of the solar constant here, and about 0.5% at the surface. The stratosphere, on the other hand, cools because it basically radiates directly to space for reasons we won't get into. So you're trapping the equivalent of like 1.5% of the amount of solar radiation. That seems kind of small in terms of 100% coming in, and in terms of leading to an unprecedentedly warm climate. And I want to try and explain why that's true without just relying on theoretical models to do that. I think the first thing to do is to compare the thermal effect the radiative effect of CO2 with the thermal effect of just burning all the carbon that you have and releasing energy, the thermal energy that you release. So if you look at the change that's going to occur over maybe the next 50 years, we're using 8 times 10 to the 12th watts, and it's going to go up about a factor of 4 in the next 50 years, according to some people's projections. If you convert this to a watts per square meter kind of use, and I'll be showing on the next slide some stuff about the CO2 effect and that. You see it's a few hundredths of a watts per meter square that you're changing. The next view graph shows, and the last one did show, I didn't do the units conversion on it, but shows that what you're really doing in terms of the radiative effect is getting up to, in the lower atmosphere, trapping more than 3 watts per meter squared, so that the ratio of what's happening, the radiative effect compared to the thermal effect, is like a factor of 80. It's kind of an incredible ratio, but that says something about how CO2 is acting in the atmosphere. And in fact, if you run a model to equilibrium, including the various feedbacks that occur, and we'll get into them, the change in downward flux at the surface is about 12 watts per meter squared. So compared to the 400ths of a watt per meter squared that you get from the thermal emissions of it, you just don't have to worry about the thermal emissions compared to the radiative emissions. Well, once one has done the radiative aspects, and as I say, I'll come back some more and try and interpret what the models mean. I want to basically talk about how we approach the problem with models to try and incorporate all the processes. And basically the models are based on the physical laws of the atmosphere, treating the land and the oceans and the atmosphere, sea ice if you have to, and things. And they treat a lot of different processes and causes and effects that are going on. And this is sort of one person's diagram of it. The next one is one person's diagram of all these kinds of feedbacks that are going on. This isn't something that we're going to try and understand. It's just to sort of show the confusion that occurs. And this doesn't necessarily include all of the things that are happening. I mean, I've added a few arrows in here. Maybe you can note they're the same color, but a lot of things were not in this original chart. They didn't have temperature affecting the composition of the atmosphere, which is something that clearly happens in the stratosphere, or the water vapor affecting atmospheric composition. There's a lot of processes going on in the atmosphere and a lot of cause-effect linkages. Some of them are really important. The one that's probably most important is the water vapor feedback mechanism, and let me just sort of go through on the next slide how this process works to amplify what's happening. Basically, if you increase carbon dioxide in the atmosphere, you increase solar absorption a little bit, but mainly you increase the trapping of the infrared radiation. So the atmosphere warms, which by radiating to the surface warms the surface, which leads to more evaporation, which is one way the surface gets rid of moisture, which leads to an increase this radiative change has led to an increase in the air temperature, and it also leads to an increase in how much water is in the atmosphere. Well, this increased warmth here will lead to increased water in the atmosphere will lead to more capture of solar radiation, because water absorbs solar radiation, and more trapping of the infrared radiation, because water, like CO2, traps the outgoing radiation. And this process will feed back on itself. And we'll go through that in a few slides about how much that actually occurs. I guess I'll come back to that. The next slide shows that there are quite a number of processes that occur this way. There's water vapor. There's the surface albedo. If you reduce the amount of radiation reflected from the surface so that more is absorbed, so if you reduce the amount of sea ice, more radiation is absorbed in the ocean, so more heat can be transferred to the atmosphere. And that occurs instead of reflecting it to space, so that there's a sea ice albedo, a snow cover albedo. Clouds can certainly change. If there are more clouds, they do two things. One, they reflect more solar radiation. The other thing is they trap more of the long-wave radiation that's coming up from the surface and re-radiate it back down. And there's a lot of controversy about what effect clouds will have in the CO2 problem. Changing the moisture of the soil changes the reflectivity of the surface. And there's some effects on stratospheric chemistry that's sort of entirely another discussion. Well, if one takes a model, and let me just show sort of the classic one. This is the first three-dimensional model result that was done by Manabe and his colleagues at the Geophysical Fluid Dynamics Laboratory at Princeton, for which I happen to have the nicest slide, I think. What happens in the upper atmosphere is, with more CO2, and the atmosphere being so thin, it can just sort of radiate more effectively to space, and so the stratosphere cools until it comes into a new radiative balance with the solar radiation absorbed by by the ozone. The lower atmosphere sort of warms 2 to 3 degrees at most latitudes, but there's an amplification of the change in polar regions. Some of this is due at least to this ice albedo feedback mechanism, because there's sea ice up there that can change. The other factor is that there's usually a strong polar and temperature inversion up here, and so instead of having to warm the whole atmosphere a lot, it really only has to warm a relatively thin layer of the atmosphere, and it doesn't take as much energy to do that. So with a finite amount of energy, you can warm the lower atmosphere even more. Some results that we get from Livermore are essentially the same. So that we do these kinds of calculations as well. We get a little bit less change in equatorial regions. There's some controversy about how much change will occur in the tropics. If you go back and look at sediment data from ocean cores that are taken this out, you find that temperatures in the tropics haven't really changed very much. And there's some real controversy about whether you'll be able to elevate these temperatures. Our model tends not to do it. The Princeton model tends to do it. But both models get similar results for a global average, and they get polar amplification of the temperature change. If you go out and look at whether this might be happening in the real world, whether you do get polar amplification of temperature changes, this is from a group in England that compared warm years and cold versus cold years. I think it's the 5 warmest and the 5 coldest years during the last century, and looked at the temperature change. Indeed, what you're getting is amplified changes in polar regions. Most of the warming is occurring in high latitudes, and not much is happening in the tropics. Part of this, of course, is going to be due to you have so much ocean in the tropics that sort of buffers the temperature change. But it really does seem to occur in the real world that you're getting an amplification of the temperature change in high latitudes. Another thing to see from this slide is that the changes are not nice zonal changes. It doesn't occur, you don't get the same changes at all longitudes at the same latitude. And so that's something that people, that the models are not yet able to really resolve. They're starting to get some ideas of that, but not doing it very well. It makes kind of a difference. And on this one, it's going to be interesting. This is a lot of warming in the grain belt, especially the Canadian grain belt. And in some places up there, they're actually limited by temperature and how much grain they can grow, and so that will be presumably a benefit to what happens in Canada. Well, not only do we get the agreement with the observation, but I just want to sort of make some comments about there have been quite a few modelers who have made studies. This is only a few of them. If this is the present natural variability of the climate, sort of varying back and forth a little bit around 300 parts per million, if you look at what happens when CO2 doubles or quadruples, most of the modelers are in sort of a band of what's happening. There are a few outliers. And one of the jobs that's going on is to try and explain why they're out there. There's a group at Goddard in New York that has some relatively high values, and in fact actually has some values that are over 4 degrees for how much warming would occur with a doubling. There are a number of people who are projecting very, very little change. One is even a global model. That particular model fixed the ocean temperatures and then ran what happens if you double CO2. That turns out to be an important simplification if you fix ocean temperatures, if you don't allow them to rise. They've since run with a variable sea surface temperature and get a number up around 2, I believe. There are some empirical studies, and we can maybe talk about them afterwards if people have read the articles in, well, this one's been in Science, and that get relatively low numbers. We can talk about those, perhaps in the questions if people are interested. The present National Academy estimate, before we go on here, is basically, we'll go back to that last one for a second. The present National Academy estimate, which just came out in a report, I'll flip it, which came out in a National Academy report in mid-July, is still 3 plus or minus 1.5 degrees for a doubling. Most of the models now are in this range of 1.5 to 3, and so I guess if I were going to make an estimate, I'd sort of put a 2.5 plus or minus 1 or 1.5 as a number. But that doesn't mean that's necessarily the right answer. That's basically where most of the modelers are, and most of the outliers can be explained. Well, let me talk a little about the mechanisms that are leading to this kind of change. The next view graph shows sort of one person's view of where the energy in the atmosphere goes, again in terms of solar units, 100 units coming in and stuff being reflected and going around. The critical issue is the infrared radiation budget, where CO2 has an influence. If you remember from the one of the previous view graphs, what I was saying was that about 1%, 1 unit here is absorbed in the atmosphere due to doubling of CO2 and about a half a unit at the surface. And the question is, why does that lead to a temperature change of 3 degrees? Well, let me just start with half a unit at the surface. The 1 unit in the atmosphere actually gets into the cycle as well, and talk about where that energy is going to go. Well, one thing might happen is you might warm the surface a little bit and let it be re-radiated to the atmosphere. Well, if you look at what happens to radiation that goes up into the atmosphere from the surface, 89 units are going up and 81 are coming back down. So basically 90% of the energy that you radiate up comes back down and you have to deal with it again. And the same thing is basically true of clouds. You're radiating up 15 units and getting 12 back, so it's very hard to radiate energy away. You have to go through this. Instead of getting rid of 1 unit, you really have to increase your radiation by 10 units in order to get rid of a net of 1 unit. Well, if you can't do it in radiation, how else can you do it? Well, you get rid of sensible heat, which is basically determined by the difference in temperature between the warm ground and the cooler air. That turns out to be very hard to change. That gradient is very hard to change. It's controlled by sort of the dynamics of the atmosphere and the convective aspect. So it's hard to get rid of an additional unit here, and so you're stuck with having to get rid of it in the evaporation process by increasing the rate of evaporation that goes. Well, where does this energy go? Well, when it goes up, some of it goes into the clouds here and then is radiated away. Well, where does the radiated energy go? Well, some goes up and about an equal amount goes down, but most of it goes into the atmosphere. Where does most of that radiation into the atmosphere go? About 2/3 of it goes down back to the surface, and so you have to deal with it again. The same is true of this. This is sort of energy that comes from the convective overturning of the clouds, and it basically heats the air that is subsiding. That ends up being energy that is in the air, and where does that go? Well, a lot of that goes back down. So basically what you're doing is just recycling the energy. It's sort of like compound interest rates. But you're getting an 80 or 90% return on your money, and it's very hard to get rid of energy from the surface. And these are the processes that are causing the major change. So if the next slide sort of summarizes the factors, the direct effects, the direct radiative effects in the water vapor that occurs because of these direct radiative effects turn out to be a relatively small fraction of the total change that occurs. Most occurs because of this intensified precipitation cycle and transfer of heat up into the atmosphere and then back to the surface. And then some occurs because of ice albedo effects. So that most of it is occurring because of these feedback mechanisms. I perhaps ought to, well, I haven't really said anything here, and maybe I ought to have a little aside to comment on whether one can really believe that the models are working and how one verifies that models are working. It turns out we don't really understand, well, we don't really have any good test cases to test the models against. We understand the seasonal cycle reasonably well and how the temperature warms and cools, but that doesn't really test the long-term mechanisms that we get into when we're dealing with carbon dioxide, where you're working about what accumulates over 50 or 100 years. You'd like to be able to use the ice ages as a test case, for example, but people don't really understand why that occurred. There's a lot of thoughts, and the prevailing opinion is orbital elements, but there are a lot of complications involved there. So there are not a lot of test cases to assure us that these models are working. And I'll come back later, I guess, to some ideas about looking for evidence of change as evidence that the models might be working. The other thing one learns from models is that not just does the temperature change, but the amount of soil moisture changes for example, because the amount of precipitation and evaporation changes. And this is again from Manabe's model and sort of a schematic of what happens. This is sort of his schematic continent in this particular model. And what he's getting is a drying out in the 40 to 50 degree latitude band, or 35 to 50 degree latitude band. What's interesting is this turns out to be the grain-growing belt of the United States, which is mainly the major grain-growing belt of the world. And so there is real concern about what this drying out may mean. And what is going on in the modeling now is to try and look at seasonal effects of this and try and refine really if it's going to be occurring in the proper regions. But if you look at past warm periods, for example, you go back to this hypsothermal, which occurred 5,000 to 7,000 years ago, you find that precipitation really did change. First in the low latitudes, these are maps of Africa, lake levels in Africa in the present and 6,000 years ago, and darker dots here mean higher lake levels. 6,000 years ago, the equatorial regions were considerably wetter, which is something that would be predicted from the CO2 models now. That's kind of interesting. And then if you look on the next view graph shows some information on lake levels in the western United States, where during the last glacial, for example, the lake levels were quite high. During this hypsothermal period, this warm period, they were very low. They got a little bit higher in between. Some of them have gotten quite dry recently, but there's still at least some lakes in some of these cases. So the sense that it will dry out in mid-latitudes and get warmer in the tropics is something that is sort of confirmed by the data as well. Another complication that we have to deal with is other trace species. There's other gases increasing, and you've probably heard about a lot of them. I'm not going to go into it, but they all have climatic effects as well. These are just various increases of these kinds of concentrations. Virtually all of them lead to a warming. And so the CO2 estimates of 2 to 3 degrees may be somewhat low just because we're not including these other kinds of factors. Will Kellogg has tried to integrate all these model results and past climate results to make a projection of what the world will really look like when CO2 doubles perhaps and gets wetter regions and cooler regions. As you can see, you got wetter regions in the tropics, drier regions in the key U.S. grain areas and in some of the Soviet grain areas. But the monsoon strength increases. So these thunderstorms that you get right now out of the monsoon kind of climate may actually, I guess, increase, but your snow in the winter may decrease, I guess. Well, has there been any has the climate changed in response to that? If you take the northern hemisphere temperature record and then you impose the CO2 projections from a model, this is what you get. This is basically the observations taken from a bunch of stations over the last 100 years, and this is what CO2 says. That's not very good agreement. And the question is basically why? Are the models wrong? There's certainly one possibility. I think what most people believe, however, is that it's other factors that have been causing the change. Let's quickly go through the next couple. But what one has to do, given that record, is to identify that climate has changed and then consider what these other factors are that may be having an effect. And then what you really want to do is isolate the CO2 effect. The next view graph shows some of these factors shows some ways of looking at past climate change. One of the real problems that exists is that there is not a good database to evaluate if the climate has changed. I showed you the record of northern hemisphere surface temperature, and there are some global estimates. There's a recent paper out, however, that gave quite a different pattern for the northern hemisphere surface temperatures based on ocean temperatures versus land temperatures. Somehow that's going to have to resolve. There's some historic information on snow melt and sea ice extent. There are reasonably good sea level indicators, but there's some complications that I'll get to. Sea surface temperature, the way everybody used to take it until the 50s is you threw a bucket overboard, pulled it up, put it on the deck, and then you measured the temperature. It turned out the bucket cooled off as the wind was blowing over it, so that those temperatures tend to be low. And the new way of doing it is you measure the engine injection temperature of the water. The water comes into the engine to cool it. And of course, it goes to the engine room, which is very hot, and that heats it up. So some real problems with that. There really aren't very good databases to deal with. The next view graph sort of shows one of the sort of the most recent, I guess, and complete global indicators. And this is the northern hemisphere again, although it's a slightly different domain. So it shows this, that it was quite cool late in the last century, and then you get this tremendous warming that occurred in the middle part of the record, and then it's starting to warm again in this person's record. A major problem is trying to understand what this is, what caused this warming. Hansen's suggestion, who created this record, is that it's due to a lack of volcanoes in the northern hemisphere. There's some real questions about that. Low latitudes, on the other hand, and southern hemisphere latitudes show an increase with some noise that is much more like what one might see from CO2. There's a real argument about whether you should be seeing an exponential change or a linear change also in the CO2 record. But you see a much more similar, well, a much more even kind of increase perhaps due to CO2. But why there would be an influence in the northern hemisphere like this that wouldn't affect the lower latitudes or southern latitudes is not at all clear. Well, let me skip the next one and go on to the next one. Well, the basic way of isolating the CO2 change then that we've got to come up with is to try and look at the CO2 results and try and basically develop a fingerprint for carbon dioxide. What are the things that have to occur due to carbon dioxide increase and the resulting climate change that are different from what happens when you have volcanic injections or changes in solar radiation or other kinds of things? Well, certainly CO2 has to increase, the tropospheric temperature has to increase, stratospheric temperature has to go down. There's some questions about, well, the infrared radiation budget has to change. If we're going to get this water vapor feedback, atmospheric water vapor better go up. There's some sense that because that CO2 will keep the nighttime temperature from becoming as cool as it does now, and there are going to be some seasonal temperature differences. But volcanoes and all these other factors also have influences, and one of the real efforts going on is to try and identify those. Let me, in terms of evidence, just look at what's happening with some of these indicators. So I just skip the next one and go on to the next one in the interest of time here. These are from Radioson data for the last about 15 years. Upper atmosphere, stratosphere. The stratosphere is indeed cooling. This cooling, however, is sharper than you'd even project for CO2. So, is that good or not? And it started to increase in recent years. Is that an indicator that CO2 is changing the climate? Not at all clear. If you look at the surface temperatures in recent years, you see that in the northern hemisphere, well, this shows some warming through the 70s. This is after the cooling that was earlier, you have to explain. So there's some warming here, but you certainly don't see an amplified temperature change in polar regions. So the indications there are rather iffy. However, the next view graph shows another way of doing the northern hemisphere temperatures from Wigley and East Anglia, and he points out that this last year, 1981, was the warmest year in the last 100 years in his way of doing the calculation, which is kind of interesting. However, maybe many of you remember this winter when January, February, March was very, very cold. So everybody's sort of waiting to see what happens in 82. It'll probably be down here again and just be a blip in the noise. Let me skip that one, I think. Maybe come back to it or something. If you look at what's happening in terms of the ice, Kukla and Gavin have done some measurements in the Antarctic, and they've actually done some measurements that go back to the 1930s based on whaling expeditions that occurred down there, and they're sort of showing that the Antarctic ice is decreasing over the last 5 or 6 years. This turns out, again, to be more rapid than what one would expect from a CO2 model. And it's also occurring in the southern hemisphere, not in the northern hemisphere, where most of the models project a larger change in the northern hemisphere than in the southern hemisphere. So there's some real doubt that has to be resolved there. But indeed, ice has changed, and there's sort of a rather famous set of pictures going back to the mid-1800s about a glacier coming down on a French town, and how in the 1960s it had retreated way back up here. So climate changes can occur and do occur and can have effects. Sea level is another thing that people have been looking at. Sea level should be rising for a couple of potential reasons, and seems to be. One is just the thermal expansion of the water. As you raise the temperature, you expand the warmer water expands, and so you should get an increase of not too different than this magnitude from just the warming of the ocean water. And so there's some real interest in looking at sea level records. The real problem with sea level records is most stations are located in places like San Francisco. San Francisco's on an earthquake fault and going up and down all the time, or it's in Sweden where the land is rebounding from the last glacial age. And so you end up throwing out about 80% of the measurements, and you're left with the last 10 or 20%, and you get this nice, wonderful trend that you think agrees sort of with what you're thinking. It's kind of a dangerous thing to do. Let me skip the next one. Let me comment finally. So I guess in summary, with respect to whether we've detected the change, well, there's sort of been some warming, and it's sort of suspicious, and one can't say there's been a cooling that's in disagreement with a CO2 increase, but there's certainly not clear evidence for that CO2 has warmed the climate at the present time. A few words on effects that you've heard about, just to close based on sort of the way I begin. The major kinds of influences are potentially on agricultural production, because you change the climate, which changes the temperature and the rainfall and how the crops will grow. There is a fellow from Michigan Agricultural Experiment Station named Sylvan Whitwer, who's a great advocate that agriculture in this country is technologically advanced enough that it can adapt to these changes by genetic changes in the crops and surviving on less water and things. So in a technologically advanced country, you may be able to adapt to some of these kinds of changes. In some of the underdeveloped countries where climate bands sort of shift right over the countries, you probably won't be able to do that. But they have so many other problems that most economists don't want to worry about. CO2 is a problem. CO2 also has a direct effect on agricultural production in that it's a nutrient that's required for plants and tends to enhance plant growth. And there's a sort of a major program starting to see if that occurs in the real world as opposed just into greenhouses where people actually grow lettuce and make it grow very, very rapidly. So that in deciding whether a CO2 increase and a warming are good or bad in terms of agriculture, it's not real clear with respect to climatic effects, although almost any change that you have to adapt to is a problem. In terms of CO2 increase, that'll probably be a help. It's hard to see how it can hurt effects. So agricultural production may not be that badly affected. The other key issue is probably this ice shelf issue, and I'll just show a last view graph on this issue. It isn't the melting of the ice that is the issue. The Antarctic is so cold right now that a little warming will allow the air to hold more moisture, and you might actually get more snow on the Antarctic continent. So it isn't the melting that is the issue. The issue is that you might not form as much seasonal sea ice. And the sea ice tends to protect the ice shelf. The ice shelf and some of the ice sheet turn out to be grounded below sea level. So if you melt back the sea ice, if you don't form the sea ice in the winter, then the water from the ocean is able to get in, the theory goes, under the ice shelf, which calves away the ice shelf, and then you lose the protection for the ice sheet, and you start calving that away. There's some suggestions that that's what happened in the final stages of the North American ice cap over Hudson's Bay, that the ice cap, that the final ice there was calved away in a time period of like 100 years because of the water being able to get in underneath. In fact, there was even, I think, on one of Walter Cronkite's shows where he interviewed where somebody suggested that was the cause of the great biblical flood. But, I don't know if I can agree with that. But so that this problem with respect to sea level is an interesting one. I guess I'll show what do I have? Oh, I have two more. This one just shows basically what would happen if you melt various amounts of ice. It's about 65 meters worth of ice up on the Antarctic on the Antarctic continent, of which only about 5 meters is grounded below sea level, and so is of potential worry. Greenland has some areas grounded below sea level too, and has a potential for about 6.5 meters of sea level. So that there's some potential for raising sea level a rather dramatic amount over a few hundred years if these theories are correct. And that perhaps is the issue that is the long-term issue of most concern. Well, I said earlier that I didn't think there was any realistic way of preventing the CO2 increase if we continue to use fossil fuel. One might ask whether there's any way of preventing the climatic effects as opposed to trying to adapt to them. There have been a number of suggestions that one go around injecting stratospheric aerosol, sulfur into the stratosphere, and create more aerosol to reflect back the additional solar radiation that you would be capturing. It turns out economically it's not that impossible a kind of suggestion. The question is all the side effects you have, and you start managing the climate in a real sense, and is that something you really want to get into? You may be able to alter the surface albedo to reflect additional radiation to space in various ways. Or you may try and take some actions in some way of preserving the polar ice and not letting it melt back. As I said, these effects that occur are sort of a mixed blessing potentially, and some of the agricultural things. A big help would be to reduce the rate of increase of CO2 concentration, basically because that slows the rate of climate change. Society is able to adapt reasonably well and has in the past to relatively slow climate changes. It's when they occur rapidly, as for example, one goes into a dust bowl situation, which is sort of what's projected if you, as CO2 sort of warms, and that's sort of what's projected for the middle US by some people. If it happens slowly, you could probably adapt. If it doesn't happen slowly, you're probably in trouble. The short-term issue that's probably of most concern in this case is water. Particularly water in agricultural areas and in the West out here where we are. In fact, in California, an issue. The Department of Energy program started 4 or 5 years ago with a financial base of maybe $400,000 or $500,000 per year. It grew through last year at a doubling each year and was up to something like 12 million last year. I'm sorry, this year it's at 12 million. It was supposed to be at 14 million. It did not suffer major cutbacks in the first phase of the Reagan cutbacks. Next year it's projected at 8 million, however, so it's getting its turn. It has basically 6 major themes that it pursues. The direct effects of CO2 on vegetation, carbon cycle research, so projecting the future CO2 concentrations, climate modeling, first detection of CO2 effects, the effects of warming on the Antarctic ice cap, which is a program that it hasn't figured out how to do, but it wants to get into. It realizes it's necessary, but it turns out almost any money you put into an Antarctic research program goes to the Navy for fuel costs to get the people there, not into science. And then the 6th one is everything else, indirect effects, everything else, effects on agriculture and vegetation. They had the AAAS preparing a major program plan in that area that included agricultural effects and social effects and economic effects, but the present administration has basically cut that way down, said the Department of Energy shouldn't be doing economic and social research. Yes?
Interested in your amplified polar temperatures in some particular parts of the geologic graph, I think specifically the Cretaceous, and I think the Eocene, you have circumpolar alligators. Has anybody looked at this with respect to the vegetation types at the time and the possible carbon dioxide effects with this particular model?
Well, no, the 3-dimensional models that most people focus on with the CO2 problem take hours to run a year, and so they tend not to run back very far. The simpler climate models that take seconds or minutes to run a year, people have tried to explain how you could have warmer polar regions. It's going to be it's an interesting question, and it is not resolved. right now you get heat transport from low latitudes to high latitudes because there is a relatively large temperature gradient. If you reduce, and that energy is needed to warm the high latitudes, even though they're still pretty cold. If you increase the temperature in high latitudes, you lose that temperature gradient, and so it's not clear why you'd get heat transport from low latitudes to high latitudes. So it's hard to understand how it can be that warm, even though there's good evidence that it was. People have looked at a lot of processes and haven't worked it out very well. It's probably related to the positions of continents and how well the oceans can transport heat up there, partly, and partly to how much CO2 existed in the world. And I think there's some Russians who have interpreted some geological evidence that the Cretaceous had much more CO2, 2 to 3 or 4 times as much CO2. And one may be able to do it that way. Not clear. Yes?
What about the timeline between when you put CO2 in the atmosphere and when it really starts warming? This one is like 20 years, or is that each year that you do this, or are any estimates out so 20 years down the line?
Well, no, it's probably something like 20 years. And that's because it takes time for the oceans to warm and for them to increase their evaporation into the atmosphere, and for that whole cycle to go on. And so basically we've made a commitment now about some more heating for 20 years, even if you held CO2 constant. That's one of the problems, and that's something that hasn't been well treated in these attempts to identify climatic change yet. Yes?
I didn't understand the effect of the water infiltrating the ice shelf, getting underneath. What is the ultimate effect of that as the water seeps in?
Well, it basically weakens the structure of it. It transports enough heat in, and I guess there's enough mechanical motions and everything that the shelf that is sitting on it just will calve away, and you'll get a gradual warming of the shelf because you can get warmer water in underneath than exists there, and you can just gradually calve it away. It's basically, I think, a mechanical issue. The strength of the ice sheet just cannot sustain sitting out on the ocean water. I don't seem to have answered your question, I guess.
So you're suggesting that the ice fractures, might fracture, but it will still float?
It will still float, and then it will float off out into the Antarctic Ocean where it will melt. Yes.
They will be transported ultimately out of the ice shelf.
Yes.
Is that likely? Considering the way you drew the profile, it seems to decline, the elevation declines as you go inward. It didn't seem highly likely that ice would float up and over into the ocean.
Well, that was sort of a schematic diagram. The ice is pinned on a number of mountains that sort of hold it in place, but there are some passages between it, so that it turns out there are, when you do simple modeling, it looks like it's going to go. When you start looking at all the complications of it really having to happen, you're not so sure. But certainly, ice sheets calving back like that is an occurrence that's observed. It's occurring up in Port of Valdez right now. There's a major ice sheet that comes down in there that has come to a ridge that has protected the ice sheet from water getting in underneath, and it's calving back, and they're expecting it to go, I don't know, miles per year or something like that back as it calves off, and they're worried about the icebergs and the oil tankers and things. Yes? I guess I'm going to beg off on that question. I'm not sure I feel competent to answer the question. I don't think the salinity changes much. I don't think that's an issue. pH of the ocean changes about half a unit, which may be an issue. Yes?
If I were going to do my part, would I plant a conifer or a deciduous tree?
Well, I guess what you want is the I don't know. It's hard, that's what I want to ask. The more you can store, the better, I guess. And that depends on where you are. Yeah. Right.
If the ocean were to rise 60 meters, by what percentage would the land surface area be diminished?
60 meters? Well,
You have
Well, yeah, no, let me make clear. The fraction that can melt, and the projections are basically 5 meters is what they're looking at. The rest tends to be grounded on land, and the assumption is it will stay there, okay, that you won't melt that. And so you have to deal with sort of with 5 meters. Now, in some regions, that's pretty severe. If you're in Florida, you're in big trouble. I mean, you're going to lose half of the state or something like that. I don't know what's regular. And if you're down along the Texas coast and some of the Caribbean coast and stuff, if you're on the coast of California, it's not going to be all that much of a problem. Some of the social questions they wanted to get into studying were how you respond to that. Walter Cronkite opened his universe show on CO2 by standing on the dikes of Holland. And the typical response is to build your dikes higher and higher and higher, because that is the least expensive thing to do on an incremental basis. However, once you get a catastrophe, you're going to be in big trouble. Then you have to relocate all at once, and that'll be very, very expensive.
Anyone has any further questions, I suggest you